Okay, so let's continue right here. Okay, constant natural frequency. Okay, basically, how do you get the constant natural frequency omega n? And this is the pose of the second order system, sigma omega d. If you take the square of this plus the square of this and take the square root, you get omega n. So basically, omega n is the radius of this circle here, right? If you get a constant natural frequency, basically you get a constant circle at here, right? So it's this circle, how this circle is being mapped to the z-plane. And as I said, we don't need to map the whole circle, we don't need this portion at here, right? So it's like we're mapping basically from here to here. And what are this value here? This is negative omega n, and that's omega n at here, right? Okay, so it's like you're going over from here to here doing the mapping. Now, one of the concepts I mentioned is conformal mapping. So when you're mapping from one complex plane to another complex plane, if in this complex plane they have a perpendicular relationship, then after the mapping, they should retain the same relationship, right? So if I draw any radial lines out of here, which is the constant damping ratio line. So this radial line is perpendicular to the natural frequency circle. So after the mapping, the natural frequency loci in the z-plane should also be constant to all the different constant damping ratio loci, right? So this is why you see in this mapping here, those curve here, this is the corresponding to different natural frequency values there, right? Yeah. Now you probably will see natural frequency. I have so many natural frequency. I can vary my natural frequency from negative infinity to positive infinity, right? Yeah. But then how come you only have this many of curves here? What's the reason? If you recall that, what is the reason? When you're mapping from S to Z, what do we call this? This is called a primary strip, right? So basically, when you're going from negative 1/2 omega s to positive 1/2 omega s, the mapping is negative pi to pi in the z-plane. So if you keep going, it'll just keep circling, right, in the z-plane. So that's why when after the mapping, okay, with a certain sampling time, of course, you basically you just go from 0 to pi, okay. Yeah, after mapping, the frequency in the discrete domain is just 0 to pi now, okay, or negative pi to pi, okay, yeah. So that's the reason at here. Now, when we do MATLAB simulation or programming, so the MATLAB has a command called the zgrid, okay, called zgrid here. So this zgrid will generate, okay, will generate a plot like this guy here, okay, like this. So this plot here, essentially is a plot, okay, of showing, okay, these different constant damping ratio and different natural frequency here. Okay, it separates this 0 to pi into 10 portions here. So 0.1 pi up to pi here. Okay, yeah, it separates into this here. Now, I'll show you one example as to how to make use of this zgrid here. Okay. Yeah. So let's make use of one example to take a look at this thing. So now let's see. Now suppose that you're in your continuous domain. Okay, in continuous domain, design specification. We have some design specification. Okay. The design specification says we want our damping ratio to be greater than 0.5. And we want our settling time Ts equal to 4 over zeta omega n to be less than 2 seconds. Okay, less than 2 seconds. So that's the design specification. Okay, design specification. Okay. So now let's do the design, and then the question is, okay, if this is the design, how is that going to be mapped, or what's the region of the pose that we can use in the z-plane to satisfy this corresponding design specification, right? That's the idea here. Okay. So first of all, you can draw, basically you can draw the region in the S-plane. Okay, in the S-plane. So settling time Ts equal to 4 over zeta n. Okay, 4 over zeta n. So that means what? So your pole for the S is negative sigma n plus minus root g at here 1 minus zeta squared. Your pole is this. Okay, your pole is this. See, this real part here is negative zeta, so that's basically here, right? That's a z. If you call this a sigma, if this is omega d, so this guy here is negative sigma here, right? It's negative sigma. Okay, yeah. So basically, we want our settling time to be less than 2 seconds, and that give us essentially a perpendicular line at here, and this guy's sigma, right, will equal, okay, negative 4 over t over s. Okay, negative 4 over t over s. So 4 over t over s, it's sigma, it's zeta omega n. Okay, and right now you want a 2, so that basically gives us negative 2. And because you want your settling time to be less than 2 seconds, so essentially it's everywhere, right, on the left side of this vertical line. So that's simply based on this specification. That's what we have here. And if I incorporate this guy here, zeta greater than or equal to 0.5, and zeta is constant damping ratio line. It's a radial line here, right? It's a radial line here. It's this one here. Okay. Complex roots always appear in a pair, so that's why I draw 2 radial lines. Okay, always compare in a pair. We want this guy to be greater than 0.5. So how does zeta define? This is theta here. So then zeta equal to sine theta, right? Sine theta. You want zeta to be greater than 0.5, meaning the theta has to be, you know, basically, if this is theta corresponding 0.5, then anywhere greater than 0.5 will be a radial line. Where is it going to be? Is that here or here? It's going to be below here, right? Yeah. So essentially, altogether, the 2 regions overlapping each other, it'll be basically this portion here, right? Sandwiched by this portion. Okay, so that's the region in S-plane. Okay, in S-plane. So then there comes the question as regarding the mapping now. Okay, regarding the mapping. So what do we, before we do the mapping here, let's look at the specific, based on the specification here, what will be the requirement on the natural frequency omega n? Okay, omega n. So zeta is greater than 0.5, and this quantity is this one here. Let's say just based on this quantity, I will be able to derive that omega n needs to be greater than 4 over 2 zeta, right? 4 over 2 zeta. Okay. So at the same time, your zeta is greater than 0.5. Your zeta is greater than 0.5. So which means you can just plug the 0.5 here, right? And then that means the omega needs to be greater than what? 2 by 0.5 and equal 4. Okay, equal 4. So natural frequency needs to be greater than 4. Okay. What does natural frequency do? What's the effect of having a higher natural frequency or a lower natural frequency of omega n here? Oscillation. Yeah. That's right. So what else does it do actually?
Faster response.
Exactly. Yeah. Yeah. So omega n needs to be greater than 4. So that's another thing. Now let's do the mapping, right? Let's do the mapping here. So when you do the mapping, basically the whole idea is z equal to e s t, right? That's your basic equation there to do the mapping. Okay? Yeah. So as we learned, if I just simply look at this, look at the drawing at here, I have a constant damping ratio. I have a constant settling time at here. So the constant settling time, this vertical line, if you recall that, any point, basically this vertical line, so it's going to be mapped to where? Okay, this is Z plane. So this vertical line here is going to be mapped into a circle, right? A circle. So because e to the power st, it's e to the power of the negative sigma omega n and ej, everything else. And this one here, it's that e negative e sigma, right? E sigma. And sigma is a constant, so the r at here, this is r. R is a constant. So you're going to have a circle basically. Okay? So you're going to have the circle. Okay. So this circle has a radius. This circle has a radius of r equal to e to the power of sigma. Okay? Or sigma is what? Sigma is -2, right? Sigma is -2. Sigma t, sorry. Sigma t, sampling time. So -2 sampling time. So let's say I'm going to pick a sampling time t equal to 0.2. Okay, so let's set sampling time equal to 1. So then you can calculate this guy here. So that'll equal to 0.67. Okay. Okay, so that's the first mapping based on this vertical line here. Based on this vertical line. The second mapping is the constant damping ratio. Constant damping ratio is mapped as a spiral, right? As a spiral. So the current damping ratio is 0.5. So this one here, your hand drawing is not that good. So we're gonna use the MATLAB. Basically, it's gonna get something like this, a spiral. Okay, yeah. Now sometimes you can't calculate some of the critical points here. You can calculate the critical points like this here. Okay, yeah. As actually this is gonna be a quarter pi if I remember correctly. Okay, at this unit. But anyway, okay. So that's the spiral here. The last one here is this omega n here. This omega n. Omega n needs to be greater than 4. Okay, omega n needs to be greater than 4. So what we're gonna have here is we're going to have a drawing, okay, of omega n, which should be perpendicular to which one? To this constant damping ratio map, right? So it'll be somewhere like this. Okay, it'll be like this. Okay, yeah. Now the question is, what will be this value here? Okay, what will be this value? That value will be omega nt. Okay, yeah, I'll show you what this means here. Okay, so this one here will be omega nt. So right now omega n is 4 and t is 0.2. So this is going to be 0.8. Okay, it's going to be 0.8. So basically what this means is when you use the MATLAB, the MATLAB will draw this, and when you see the number here 0.8, so then you can use that number divided by the sampling time t to give you back the original continuous time of natural frequency omega n. Was that clear? So if I go back to this drawing here, see that here? This is 0.2 pi over t here, right? 0.2 pi over t. So basically all this means is your natural frequency at here is that number 0.2 pi over the sampling time t. Now maybe it's somewhere here. Then what's the corresponding natural frequency? And it's probably 0.25 over capital T. Okay, so whatever value that on the circle divided by the capital T, the sampling time, give you back your original natural frequency omega n. Okay, yeah. So in this particular case, that's going to be 0.8, and for this constant damping ratio, you have the mirror part on the other part from negative pi to 0 part. Okay, so there we go. And that's essentially actually my drawing. What I'm drawing here? Sorry, I draw around here. this is not 1 here, right? This is only 0.67 here. Number 1 is here. Your spiral always starting from here, right? The spiral starts from here. Okay? Yeah, the spiral starts here. Okay, spiral starts here. Okay, so then my natural frequency at here. Okay, it's going to be different now. Okay, it's going to be different now. This is 1 at here. So the natural frequency here will cross right at this point. Okay, will cross right at this point. And your unit circle is here. Okay, your unit circle is here, and this is 0.8. Okay, unit circles are point here. Okay. Yeah. So I'll show you what the MATLAB will. I'll explain what the MATLAB here. Okay. Yeah. Before we move on, maybe I should mention one more thing here, just a little bit. Just a little bit here. Okay, so let's come back to the constant natural frequency here. Okay, think about this circle. Let's look at this special point. Look at this point here, right at this location. So if you draw radial lines out of everywhere, that's constant damping ratio. If I draw a line right here, so that's basically kind of special here, right? Why? Because this is on the g omega axis. Okay, on g omega axis. When this is on g omega axis here, there's omega n at here. So your sigma is going to be 0. Basically, real part of the roots is going to be 0. There's only imaginary part. If there's only imaginary part, as a matter of fact, if you recall that, if I draw a horizontal line at here, okay, so all of this line will be mapped into where? All of this horizontal line will be mapped into, of course, Z plane. Let me just draw this one here. Okay. So this is omega n at here. This is the radius, the constant natural frequency. Okay, yeah. So for this point A at here, point A, the real part is 0. Only the S is just g omega n. Then after the mapping, where is it going to be? The Z is EST. And that equals just the Eg omega nt, right? Eg omega nt. So basically, it's going to be mapped into the Z plane. And where is it? What's the radius here? The r will equal to 1. So it's going to be mapped to the unit circle. If this is the unit circle here, and where is it going to be mapped to? With the angle of omega nt. So it's going to be mapped over here. And the angle here is omega nt. Was that right? Okay. So my point here is, okay, so I'm going to use this circle here. Okay, I'm going to use this circle here. Suppose that it's going to be mapped, okay, omega nt on the circle here, right? Let's say maybe the omega nt, I'm going to connect, yeah, this is a little bit too messy here. Okay? Let's say that let's say this is my omega nt here, okay? This happens to be this angle omega nt. Okay? Yeah. So I want you to use this conformal mapping here. Look at the relationship. Okay, look at this relationship here. So what happens is this line represents the constant natural frequency, right? This curve, which is perpendicular to what? To each one of these constant damping ratio. So this guy here will perpendicular to this circle here, right? To this circle. And this line at here, okay, this line at here, actually, if I come back here, so this guy here, if I draw a horizontal line here, that basically give me these radial lines, right? Give me these radial lines. So this radial line is also perpendicular to this circle here. This is the unit circle 1. Okay? Can you see the relationship? So this line here perpendicular to the unit circle. If I come back here, so this line is perpendicular to the unit circle. And this constant natural frequency is also perpendicular to the unit circle at this location. So that means this radial line and this constant damping ratio, constant natural frequency, they should be tangent to each other. Okay? Is that good? Right? So they should be tangent to each other. So when you connect here to here, that should be tangent here. And the corresponding angle here, that's omega nt. Okay? That's omega t. Basically the value at here. Basically the value. So if I look at this, what I have here, if I draw it correctly, and this value is 0.8, then this angle here is 0.8. Okay? It's 0.8. Was that good? Yeah, there's a little bit detail city here, right? A little bit detail. But I want you to practice MATLAB to draw this in here. So here's the code here, okay? So just to kind of go over the, I'll explain what I does here. Okay. TS sampling time, zeta damping ratio 0.5. Omega n is to calculate the natural frequency. Okay, so natural frequency here. Why is the dot to there? Okay, omega d, and that's basically the damped natural frequency. Okay, t is the sampling time, and capital P at here is to calculate the desired pole at here. Okay, to calculate desired pole. So what is a p? That p basically it's a p equal e to the power of negative zeta omega n and ej omega d. That's p. Okay, yeah, let's calculate desired pole. Basically, based on your zeta, based on your omega n or omega d, okay, you calculate this capital P, the desired pole location. Okay, yeah. So that pole location is actually basically the intersection of this and this location here. Okay, location. Okay, yeah. So then we can use a z-plane. So z-plane command, plug in the pole here. So this should be conjugate here. Plug it here. The first one I used just the quote, just a single quote. Okay, this is not a double quote. It's a single quote to get rid of this first. I don't need to enter the first. I guess we don't have a zero here, so I only need to show the pole. So with z-plane here, generally would show you the location of the zero and the pole that you want. So in this case, I don't have a zero, so this is why there's nothing at here. Okay, yeah. Okay, so the z-plane will draw the location of these two guys here, and then we use the z-grid. So the z-grid is what I showed you in the previously, but we're not drawing every one of them. So we're only drawing the corresponding 0.5 spiral and also corresponding natural frequency omega nt. So this is 0.8 here. Okay, yeah.
So the 0.8, is that supposed to be slope or angle?
Which one? This 0.8 here?
Yeah.
0.8 is its omega nt value. Natural frequency times the sampling time. Oh, what's the unit for this one here? Omega n is reading per second, right? So t is seconds, so that should be reading, it's a degree. I mean, reading here. Yeah, so it makes sense, right? So when you draw this one tangent, so that's actually basically reading. Okay, angle represents. Okay, yeah. So when you make use of z-grid to draw these things here, Okay, this is what you should do. Okay, make sure the second parameter here, the first parameter is the zeta. The second parameter should be the omega n times your sampling time. Okay, that's actually important. Okay, so MATLAB does this normalization right here. Right? Yeah. So after this drawing here, as you can see, based on our specification, right? Based on the specification, what do we need? We need my zeta greater than 0.5. We need my omega greater than 4, right? We also need the settling time to be over here. Over here meaning we need it to be within this circle here, right? So we need it to be within this circle. Hang on a second, I missed a circle here. Just a second, I think another one here. Now this is the example. What are we looking at here? Okay, that's the unit circle, and this circle is the circle corresponding to the settling time, and this is the 2 spiral. So we need it to be within the circle, and we need it to be greater than 0.5 damping ratio. Greater than 0.5 meaning has to be below this one here, because what's the damping ratio corresponding to this unit circle here? Damping ratio at this unit circle location is 0, right? It's a 0. Okay, so when you're going out here, you have a less and less damping ratio. Okay, and we need natural frequency to be greater than 4. So in the low C point of view, and we need it to be actually on this side of this curve here, right? So altogether, you have this shaded area, and that's the location you can pick a pole to satisfy the design specification. All right? Yeah. So check out this MATLAB file. I'll upload this one here, and how you properly draw a circle. The shaded areas, and actually, I didn't figure out how to draw it in MATLAB, so I just manually in Word draw it here. Okay, yeah. But get a hand of how to make use of the zgrid, the z-plane together to draw these things. Okay, yeah. So I think I have time to go over the observer now. Any questions? All good. Just quick final words here. So in the end, right, the mapping is all about an idea of how the system behaves. So this diagram here shows you is basically impulse response of different poles in the S-plane. So on the right side, apparently they are not stable, right? They're not stable. On the vertical axis here, G omega, they have a constant oscillation. And when it's on the left side, they're stable. On the real axis, just a decay. If a complex number poles, then you have oscillation, right? So that's S-plane. So after the mapping, we can create a similar diagram for the Z-plane. So for example, if this is the point in the unit circle in the Z-plane, apparently it's stable, right? It behaves like that S-plane there. If on this side here, okay, so basically negative real part, you will have lots of oscillations as shown in this guy here. So you see, when you have a negative 0.9, you have oscillations here, right? And that's actually negative pi or pi. That's the highest frequency here. So in general, in the Z-plane, we call this portion is high frequency here, and this portion we call the low frequency at here. Okay, yeah. All good? Yeah. So check out this diagram here, getting hand of what's the effect of different locations of the poles there, right?